again, for the right operation, you need to turn on these access transistors. And you drive this bit line and bit line bar to either like 0 and 1 or the other way, so that you can override whatever value you have inside. Okay? So you are, let's say you originally had 1 on this node and 0 on this node, here and here. And then you are writing 0 and 1. Then basically you are overpowering this. So originally this PMOS is pulling up, but you pull down. And originally this NMOS is pulling down, but you should somehow pull up this node. But in reality, the right operation is actually done by this side. Okay, when I say this side, that means right operation is actually done by pull down operation, because your access transistor is actually NMOS here, right? If your access transistor was PMOS, you could do your right operation by pulling up, but with NMOS, you can't really pull up much. You remember this, right? So what happens here is you originally have 1 and 0 here, 0, 1 here. What's happening here is you drive this internal node A to ground through this transistor N2, and you are fighting against this pull up PMOS, P1 here. So P1 is pulling up this node A, but you are pulling this down. And you can actually win. Your N2 can actually win this, and you should win this fight. Whereas on the other side, this is 0 and this is 1, but the current injection through this NMOS is relatively weaker. So if you actually look at the graph, actually let's say this is A and this is A bar, then initially A was high, and as you enable your word line, your A goes down first, and then your A bar flips. So that means this node, this 1 goes to 0 first, and then that turns on this P2, and that pulls up the A bar. That's what's really happening. Okay? So for right operation, you should look at what type of transistor is used for access transistor. And here, access transistors are NMOS transistor. That means you are writing by pulling down internal node. So that means when you want to pull down, like when you want to pull this node A down through this N2, then this should be stronger than P1 pulling it up, right? So, or on the other words, this should be stronger than P2 pulling it up. So, you should be able to overpower, right? So that means your N4 should be stronger than P2, or your N2 should be stronger than P1. That's required for right operation. So let's look at how the right operation, when the right operation is happening, how the internal transistors are behaving. So again, okay, this example is opposite. So now we are assuming this A bar is 1, A is 0. Okay. So originally we had PMOS here, but this is connected to VDD. NMOS here, this is connected to ground. So you delete these two. Okay. And you only put these transistors here. And then what's happening here is you are pulling this down. So this is 0, this is 1. So this internal node is pulled up by P2 and pulled down by N4. So you have to win this fight. On the other side, you could also inject current by through this N2, but basically this is NMOS driving high and this is NMOS pulling down, so you can't really win, this cannot really win this. So you actually need to flip this first and then let that feedback comes to here and let this pull up happen. So again, you need, so yeah, this is again, what is this voltage you can pull up this node on this side, whereas, oh no, P2 and 4. Okay, so how low this graph is. Okay, I think this is kind of flipped, but basically here what you want to do, what you want is you have to make sure that your N4 is much stronger than P2, and that will give that will make sure you can pull this node down strong enough. I'm not sure why this graph looks like. Okay, let me figure that out later. But on the read case, what we wanted is we want to make sure N1 is stronger than N2. So between these two, we have to make sure this is stronger. But on the write case, what we want is, let's say this is P1 on this side. On write case, what we have to make sure is N2 is stronger than P1 here, right? So this is for read, this is for write. So for SRAM, you have to size it this way, so that read and write operation can happen can safely operate. So same way we can think about the static noise margin for write. Actually for write operation, we do want to flip the voltage, right? So we actually want to flip the voltage. So that's actually different from the original case. So let's think about this case where you originally had stored 0 and 1 on this node, but now you actually want to write opposite value, which means you are driving 1 on this side and 0 on this side, okay? So originally your inverter 1 VTC would look like something like this, right? However, again, we had this current injecting NMOS here, right? So from the read case, we know that this would look like something like this. This goes up, right? How about the other side, node V1? This inverter 2 originally had this, right? Inverter 2. But for inverter 2, what this access transistor is doing is, if your inverter 2 output is high, if this node V1 is high, it's pulling it down. So when your V1 is high, like this region, it will pull it down. So that's why you originally had this, but now your VTC goes down like this. That's why your inverter 2 VTC looks like this. So if we summarize, inverter 1 VTC is changing like this. Inverter 2 VTC is changing like this. So originally we had overlapping region here, right? That way we could stay at this point. We had overlapping area here, we could stay at this point. Now inverter 2 VTC is going down here, so there's no overlapping point anymore, right? So we have to go this way. And that is how writing operation is happening, right? So that makes sense. So in write case, we can in similar way we can think of a square which is biggest and which fits in this area, and you can think of this as a write noise margin. So if you back off by this much and this much, let's say your inverter 2 goes like this, your inverter 1 VTC goes like this, inverter 2 goes like this. Now you start have overlapping area. So that means you can actually stay with the original value, which is not what we want, right? So now this can be actually the noise margin for write operation, right? So unless we have noise voltage, if we have noise smaller than 0.21 volt, we should be able to write. Okay, because there's no overlapping area on this side. We should go that way. Okay, I think I was hurrying because this is the last lecture and I